So we are given an initial velocity of 50 meters per second. And I know the golf ball's on a tee, but we're assuming that it leaves the ground from the horizontal at an angle of 30 degrees. And we are also told that there is a fence 12 meters high, and that fence happens to be 200 meters away from where we are striking the golf ball. So we are asked to find a few things. One, we need to know how long does it take the golf ball to reach the fence, so we're going to be looking for the time. We also need to know if the golf ball is going to strike the fence or pass over it. So we don't really know what path it's going to take, if it's going to land past it or if it's going to kind of fall down and strike the fence. So we're going to need to know what that vertical height is 200 meters away. And then lastly, we're asked to plot the various components of the velocity versus time. So let's get started. Remember, when you are given a projectile launched at an angle, it's always helpful to find the components of the velocity first. So we're going to do that now. So you can either pause the video and come back and check your answers, or you can kind of follow along with me. So for our horizontal component of the velocity, we're going to take that initial velocity of 50 meters per second and multiply by the cosine of the 30 degrees for that angle that was given. And we should end up with a Vx component of about 43.3 meters per second. And our vertical component of the velocity is approximately 25 meters per second. Now we can use this to figure out the time that the ball's in the air. So remember, we struck the golf ball, there's a fence, and we want to know how long it takes to reach those 200 meters. So even though that may not be the full range of our golf ball, we are looking at a range of 200 meters away. So we can say that our x value is going to be 200 meters. We know what Vx is, and we're looking for a time. So that allows us to use that x equation of x equals Vxt. From this point, we can plug our numbers in and find out how long it's going to take for that golf ball to reach the fence. So let's go ahead and do that. So once we plug our numbers in, we simply need to divide, and you should get a time of about 4.62 seconds. Now remember, this may not be the entire time the ball's in the air, but it is the amount of time to go from where it's struck to travel those 200 meters horizontally. Next, we need to know what the vertical height of the ball is going to be after those 4.62 seconds, and then compare that to the height of the fence. So since we are looking for height, we're going to use the y equation. So I'm going to go ahead and rewrite that for you. So when we plug our numbers in, we already found what that vertical component of the velocity was. It was 25 meters per second. And I'm going to leave the units out just so I don't run out of room on the screen. And then the time that we're using, because we're looking for the height of the ball after it's traveled those 200 meters, we need to know what that vertical height's going to be at that point. The time we found in part A was to travel all the way across somewhere to that vertical area. So we are using the full value of the time that we found in part A. So I'm going to go ahead and put in my 4.62 seconds. Then we're going to add 1/2. Gravity is still negative, so we want to plug in negative 9.8. And then our time is 4.62, and don't forget to square that one. So I'm going to write in a couple of extra steps for you, but you can go ahead and calculate this out on your calculator and see if we come up with the same answer. Hopefully you got a vertical height of about 10.9 meters. And remember our picture down here on this point on the fence. Let me redraw that for you so it's a little bit clearer. Remember our fence was 12 meters tall. Well, we know after those 4.62 seconds, our projectile, our golf ball, is only going to be 10.9 meters tall. So it does in fact strike the fence. And lastly, we were asked to graph the components of the velocity. So I'm going to pick a new screen and we'll draw those graphs. In part C, we were asked to plot the horizontal component of the velocity versus the time. And I hope you remember from those pictures that we've had on the board that there is no change in the horizontal component of the velocity. So when you're asked to plot this, you know that since there's no acceleration in the horizontal direction, that means that horizontal component of the velocity is going to remain constant. So we would draw a horizontal line because it does stay the same for the entire flight time. And you are also going to be expected to fill in a value for where that crosses the y-intercept. So our initial horizontal velocity, remember, was 43.3 meters per second. So you would label that point as the value for the horizontal velocity to show that it doesn't change for the entire time interval. Now let's do the vertical component. Also, on the board in the classroom, we had pictures of the vertical velocity vectors as they traveled along a trajectory. So remember, for our initial velocity in the vertical direction, we did start at a positive 25 meters per second. And down here, I'm just going to write you a little bit of a reminder of what those vectors look like as we traveled along our trajectory. We started out with a large vertical velocity, then it got a little bit smaller, and then a little bit smaller, and then there was nothing halfway through the flight, and then those vertical components matched symmetrically, but they changed their direction. So gravity is acting in the downward direction. So as our golf ball travels upward, that velocity is getting smaller because gravity is working against it. At the top of the path, that's the point where it stops and turns around vertically. And then gravity is going to make it accelerate on its way downward. So what we want to do is show the initial vertical component of the velocity, which we did up here at the positive 25 meters per second. And we know that it's going to be in the air for 4.6 seconds, but we need to know the actual time that's going to be the halfway point for that maximum vertical velocity. So we actually do have another calculation we need to make first so that we can label our time axis correctly. So a couple of things that we know: the slope of our velocity time graph is going to be equal to the acceleration, and in this case I'm going to round a little bit. I know it's negative 9.8 meters per second squared, but we're just going to approximate and say that we know the slope should be roughly negative 10 meters per second squared. And then we can use our kinematic equations to figure out what that velocity is going to be at the maximum height. In this case, we know that the final velocity from that first kinematic equation is going to be 0 because we started at positive 25 and it's going to be 0, and we want to know how long that's going to take to happen. So I'm going to plug in a 0 and then 25 for that initial vertical velocity plus, and I'll go ahead and put in the exact value that we use for gravity for our acceleration. And then the time is what we're going to be looking for. So I end up with negative 25 equals negative 9.8 t. And this lets me know that I'm going to reach that final velocity of 0 at the top of my path after a time of about 2.5 seconds. It was 2.55 seconds. And remember, if we were to round and just kind of look at a generic slope of negative 10, we should see about a 2.5 second spot where that's going to have 0 velocity. So let me get a new screen and get a clean graph for you. Remember, we start out with a positive velocity in the vertical direction of 25 meters per second. We know that that velocity is going to decrease steadily because gravity is a constant, and it should reach 0 meters per second for that vertical height at about 2.5 seconds. And then that slope continues, and we don't know what's going to happen after it hits the fence. We're not really interested in that, so we're just going to end our graph at the time interval until it hits the fence. So we would end it at 4.62 seconds. And you should end up with a slope of around negative 10 meters per second squared. For our second example problem, we're going to have a place kicker kicking a football, and the idea is that the football is going to be 36 meters from the goal, and it has to clear the crossbar, and you're given the height of the crossbar. We know the speed and the angle at which the ball is kicked. First, we're going to have to find the vertical and horizontal components of the ball's initial velocity. So remember, that's always what we want to do first, so we have those extra pieces of information. And then we're going to figure out the height of the football after we know how long it's in the air, and figure out if it clears or falls short of the crossbar. So do they actually make the field goal? And then also we want to know if the ball is approaching the crossbar while it's still on the rise or while it's falling. And then we're going to be asked to sketch the components of the velocity versus time again. So remember, it's helpful to draw a picture, so I'm going to do that first. So let's look at our picture. We know that there is an initial velocity of 20 meters per second, and the ball is kicked from the horizontal at an angle of 53 degrees. We are told that the horizontal distance to the crossbar is 36 meters, and we know the height of the crossbar is going to be 3.05 meters. So first we are asked to find the vertical and horizontal components of the ball's initial velocity. So I'm going to go ahead and do that at the top of the screen. And you should come up with values of 12 meters per second for the horizontal part of the initial velocity and 16 meters per second for the vertical component of the initial velocity. So part A is done. Let's move on to part B. Next, we are asked to find by how much does the ball clear or fall short of the crossbar. So we actually need to know how long it's going to be in the air to reach that crossbar that's 36 meters away. So we know our x value is 36 meters. We found the horizontal component of the initial velocity, which was 12 meters per second. And before we can figure out the height, we need to know how long it's in the air to travel those 36 meters. So let's use our x equation and plug in and find the time. You should have gotten a value of 3 seconds that the ball is going to be in the air until it reaches the crossbar that's 36 meters away. So we can use this information to figure out the height of the actual ball at that time. So we're going to use our y equation. I'll go ahead and write that in for you. So remember, when we're looking for the particular height in question, it's going to be the height of the football at those 3 seconds. So we don't need to do anything to the time when we plug in those values. So let's go ahead and plug in our numbers and find out what the height's going to be after 3 seconds. Remember, gravity is still negative, so you want to plug in a negative 9.8, and you should get a height of 3.9 meters. And it wanted to know by how much does the ball clear or fall short. Since this height is taller than the 3.05 meter crossbar, we do know that it clears it, and then you would simply subtract the difference to get the height that it clears by. So we should end up with it clearing by a height of about 0.85 meters. And I did make a note when I was working this, depending on how much you round, you may have gotten up to 0.89 meters, and then also maybe 0.77. So somewhere in that range, but it definitely does clear the crossbar. And with these digits that we used, carrying out those sig figs through, you should get it clears the bar by about 0.85, somewhere in that neighborhood. And our next question is if the ball approaches the crossbar while still rising or falling. So in this case, we would want to figure out if that vertical component of the velocity after 3 seconds is going to be positive or negative. So if it's positive, it's on the rise, and if it's negative, it's going to be falling. So let's look at an equation for us to calculate and see what we come up with. I'm going to use that first kinematic equation. And in this case, we're looking for a final velocity after the 3 seconds. So we started out with an initial velocity of positive 16 meters per second. Gravity is a negative 9.8 meters per second squared, and we know that the ball was in the air for 3 seconds. So once we plug those numbers in and calculate, you should see that we do in fact get a negative value for that final velocity. So that tells us after 3 seconds, if that velocity is negative, then it's actually on the way down, and we know that the ball is falling at that point. Alternatively, you could have calculated the entire time that the ball was in the air. So if we had looked at if it were to land on the ground at the same height that it started, you could have calculated the total time in the air and then looked at the time that it takes to reach the 3 seconds and see if that's in the first half or the second half of the flight. So let me write that out for you on a new slide, and then you can go back and compare and see which method you prefer. So again, instead of finding that final velocity after 3 seconds and looking if it's positive or negative to tell a direction, you could have also calculated the total time the football is in the air, so the total time it takes to complete the trajectory, and compare that time to the 3 seconds it takes to reach the crossbar. If the 3 second mark is in the first half of the flight, it would be rising, and if 3 seconds occurs in the second half of the total flight time, then the ball would be falling. Now let's do our graphs. I picked the horizontal component of the velocity versus time graph first, and I'm hoping by now that you know that the horizontal component of the velocity during a trajectory does not change. Remember, there's no acceleration in the horizontal direction, so that horizontal component of the velocity does not change during the flight. So we should end up graphing a horizontal line. And on the AP exam, you'll also be expected to provide some numbers. Make that a little bit straighter. So we know that the initial horizontal velocity was a positive 12 meters per second. And we also know that the flight time, for our purposes, is going to end at 3 seconds. So you should have a horizontal line crossing the y-axis at positive 12, and it should go out to a time of 3 seconds. Remember, the vertical component of the velocity is going to change. It's going to start out positive and large, so we're going to go ahead and label our initial vertical velocity at positive 16 meters per second. We also know that it's going to end after 3 seconds. That vertical velocity does change. It's going to shrink down to 0. Sorry, that should be a straight line. I'm not very good with the stylus. And then we know that it's going to continue in a straight line until it hits the 3 seconds. But we can also figure out a few more numbers. In that previous section, we know that we found a negative final velocity, so we can actually label that point on our graph as a negative 13.4 meters per second. We know that that's where that ends. You could also figure out that the time at which it crosses would be about 1.63 seconds. Remember, the 3 second time interval we found was not the entire time of the flight. It was only to reach the goalpost. So we cannot simply divide that time in half. We need to know where it's going to cross on that actual axis. And one way we could do that would be like we did in the previous golf ball question. So let me go ahead and write that out for you. We want to know at what time that velocity is going to turn out to be 0 seconds. We have the initial vertical component of the velocity. We know our acceleration is due to gravity, so it's negative 9.8. And if we solve this, you would see that we reach a velocity of 0 meters per second after 1.63 seconds. So that's how I would know to make my line cross at the x-axis at 1.63 seconds, because that's when it would have 0 velocity. And then remember that it's in the negative direction, so our velocity would be in this part of the graph for that later part of the flight, and then it does increase in value because gravity is making it accelerate.